So let me tell you a bit about me. So I come from Niš, Serbia, where I did my bachelor's, and I in an electrical engineering faculty, but computer science, courses, right, direction. Then I moved to Milano, where I did my master's and also PhD with Carlo Ghezzi. Unfortunately, did not overlap with the Carlo, who did it before me, but I had a wonderful time there. And then I moved to ETH as a first postdoc and then Ober assistant, working with the Professor David Basin in the information security group. As Carlos said, my interests are kind of broadly at this intersection: software engineering, formal methods, and security and privacy. And over the last 10 years, I've worked on various different topics in these three fields. With runtime monitoring or runtime verification, I would say encompasses runtime monitoring and enforcement being the main focus. So let me start with some motivation. So here are some examples of data breaches, which are high impact examples with millions of dollars of costs, where the problem was that access control was either misconfigured or misimplemented correctly. And access control is an instance of runtime enforcement. We can also conclude that access control is very difficult to implement and evolve, as is usage control, you see here, which is actually similar to data protection. So access control with additional obligation on how the data that is being accessed is used currently. So this is kind of the motivation why I'm developing these kind of techniques, because these techniques would hopefully resolve many of these problems. So what is runtime enforcement? Given a system, here represented with this acronym SUS as a system under scrutiny, which can interact with some environment, the system provides an observable step that it takes to in a form of events. Here, for instance, a set A of possible events, capital E, which constitute a sequence, which we call a trace. So here we have a trace of sets of events, which are then given a policy, for example, some legal provision, received by an enforcer, which will then check this policy against this trace and provide commands. So it would react to these events and provide a reactive command to the system, which will then need to correct its behavior based on the commands to be policy compliant. So this is a high-level idea of runtime enforcement. Now, there are some details there. So given a policy, the predicates in the policy will correspond to events in the system, and some of the events, depending on the domain, will be causable. The enforcer can ask the system to do them, or suppressible. The enforcer can force the system to not to do them, right? Based on that, the reactive command will then consist of subset of the events that were observed that need to be suppressed, and an additional set of events that need to be caused. Now, if we move to first order runtime enforcement setting, these events may have parameters, and of course the causable and suppressible events as well. These parameters can be drawn from an infinite domain of values. Furthermore, real-time first-order runtime enforcement deals with also timing constraints. So timing can also exist in as part of the events. So we can have a timestamp when the events occur. They can also be relevant for the policy. The policy may constrain within what time certain events can happen, in which order, for instance, also absolute order. And the enforcer itself must react in real time in order to provide these commands and make sure that the timing, the policy is preserved time-wise. Now, of course, there is another type of enforcement called proactive enforcement, which is in contrast to what we've seen so far, where an enforcer doesn't really need to react to anything the system does, but rather only to the change in time. And this is crucial for enforcing some types of policies which consist of obligations, something that needs to happen in the future. In these cases, the enforcer just prompts the system under scrutiny with a proactive command, which consists of causable events that needs to happen. Here is an example of a policy. I draw this from a data protection domain. So a data subject should have the right to obtain from the controller the erasure of personal data concerning him or her without undue delay. To formalize this, first of all, to enforce this, we need to formalize it. And to formalize it, we need to kind of distinguish what undue delay means. But then we also need to distinguish different users whose data we need to ensure are erased upon request, which requires us to use first-order constructs in our specification language. We need to capture real-time delays because of the undue delay. So we need real-time enforcement. And also we need to erase data when the undue delay is elapsing, which requires proactive enforcement. And this is also similar for other data protection requirements, but also for other things like real-time kernels, firewalls in other domains. This is also quite often the case. So what I would cover in this talk is essentially an algorithm and a tool that can do proactive real-time first-order enforcement of a specific policy language called metric first-order temporal logic. Can I get a sense of the room? How many of you are familiar with temporal logic? Okay, good. So I have some slides prepared. So I will introduce what metric first-order temporal logic is, and then also introduce a fragment of the logic that is actually enforceable, because it is possible that certain specifications are not enforceable given the capabilities of the enforcer. For example, a trivial example would be if the enforcer needs to suppress passage of time, this is not enforceable, right? Then I will explain an enforcement algorithm for this fragment. Then I will tell you about the instance of the implementation of that algorithm called enfguard, the tool, and show you some empirical evaluation on some data sets. Okay, so metric first-order temporal logic, it's a logic, right? So it consists of grammar, syntax. It is similar to a normal propositional logic, except we additionally can quantify over the terms that appear in a predicate, which is the first case in the lower grammar. We have negation, we have conjunction, and then we have these temporal operators. The filled out circle is called previous operator, and it refers to exactly the previous step in the computation of the system. The white circle is next. It refers to the exactly next position in the computation. And then we have since and until, which refer to a certain pattern of behavior where the left-hand side repeats until the right-hand side happens. Or in the case of since, it's, if you look backwards, dual. So the left-hand side repeats since the right-hand side happened. Okay. Here is the semantics a bit more formally. It's on a trace, which is a sequence of timestamps at sets of events. Time point, which is an index in this trace, and a valuation, which is just a mapping from variables to the main elements. So such a valuation index trace satisfies the formula if there exists some position in the future, satisfies an until formula, if there exists a position in the future where the right-hand side is satisfied, and the differences in timestamp belong to an interval that is here in subscript of the until. And then from that current moment, including the current moment, until that moment where the right-hand side formula is satisfied, excluding it, there is a sequence of left-hand side satisfactions on the same trace. So something like like this pattern: phi, 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 psi, where phi is the left-hand side and psi is the right-hand side. And of course, psi occurs with a timestamp difference, which is within the bound AB. Clear? Okay. There are also a lot of derived operators Mostly Boolean ones are, I guess, well known, and as well as for all quantification, which is that negation of the existential of the negated formula. But then we also have this thing called once operator, which is a since with a true set on the left-hand side. It just means somewhere in the past, this formula held. Globally in the past, which means always in the past, this formula held. And I guess both versions for the future. So eventually in the future, eventually always in the future. Of course, if I say a trace satisfies the formula, I mean for any evaluation and at the first time point, at the first index. Still have you following? Feel free to interrupt me if you have any questions. Now, how would we formalize this example? We would concretize the undo delay with 30 days. And then we essentially have whenever a user U requests the deletion of some data D, then we need to ensure that this data D is deleted within 30 days. This is the simplest proactive case of enforcement. This is how the policy would look like. So it is always the case that for all users and all data, if we observe a deletion request by a user for some data, then within 30 days, the data is deleted. Now, we would need to see if we can actually enforce this formula, and I will claim that we can, because it belongs in a fragment of enforceable, which we deemed is safe to enforce. This fragment is, so the enforceable, semantically enforceable formulas are actually undecidable. The set of these formulas is undecidable. So this is actually an under approximation of possible formulas that we can enforce. What we do is we essentially do some type checking on the formula. So these are type rules. A typing judgment, which is of the form gamma entails phi of type alpha, means formula phi types to alpha in the context of gamma. And we say that the formula is enforceable, or in this fragment enforceable, if there exists a typing judgment such that the formula is causable. C. So we distinguish between C, which is causable, and S, which is suppressible. And this is essentially what our typing context is a mapping from events to either this event is causable or suppressible. So if we have a simple predicate, this predicate is causable whenever the event is in the system is deemed causable. So we essentially have to know in advance which events are causable. Similarly, for suppression. For negation, it's kind of interesting. We just flip suppression and causation. So if a formula is suppressible, then its negation is causable, and vice versa. For existential quantification, if a formula is causable for some assignment of free variables, then we can for sure cause it for one of them, right? So I'm reading this top to bottom. And then there is this interesting case where if a formula is suppressible, I mean, if you think about it, we would need to suppress it for all possible valuations, right? So in order to claim that we suppress the existential quantified version of that formula, we would need to be able to suppress it for all values that variable can assume. And this could be infinitely many. So what we do here is we actually have another set of rules that define whether this subformula is past guarded, meaning that all assignments to the variable x come from what has been seen in the trace in the past, including the current position. And this is a way we can support suppression of this kind of formula. And of course, if something is not past guarded, it's rejected, and it's not enforceable. For conjunction, it's easy. If you can cause both subformulas, you can cause the conjunction. And if you suppress at least one of them, you can suppress the conjunction. For since, you can of course cause it. If you can cause, so since is the version in the past, right? So you have 555 psi in the past. You can cause the since by just causing the right-hand side at the current point, and 0 is in the interval. And that's the only way you can cause since. You cannot change the past, right? The other way to suppress since is you can suppress the left-hand side if 0 is not in the interval, which means you may be in the situation when there is a chain of phi's with a psi, and then you just block phi because psi is maybe in the interval in the back. The other option is if you have 0 in the interval, then we need to be able to suppress both sides of the formula to ensure that we are suppressing the since. And the similar idea holds for until and for next, and previous is the only operator that cannot be enforced because it really talks strictly about the past. So how does this work for our formula example here? So I claim if a deletion event is causable, meaning I can instrument the system such that when I send it a command to delete something, it deletes it. Then this formula is enforceable. And I can show you by typing using these rules. And these rules are actually not the same rules as the one from the other the slide, but are derived from them because these are rules for these specially derived operators. And you can easily derive them by just applying the unrolling of the operator based on the definition and then applying the rules. So these are just very specific rules for these derived operators. So here is how it looks. So gamma contains a mapping delete to causable, and that it types this formula to causable. And now we are proving this, so we are doing backwards reasoning. We apply the for all rule. The for all rule tells us that the subformula needs to be causable, and we need this past guardedness thing, which we derived from the existential rule for suppression. So it's the opposite. Then we apply the for all rule again, and we have the same thing, and we now removed the two quantifiers. And then we apply an implication rule, which you can see here, and that means you can cause an implication by causing the right-hand side. Because if the left-hand side is not true, the implication is true anyways, right? So we just need to focus on the right-hand side. So we need to cause delete, eventually delete. And then for the eventually, we just need that the interval is bound, which it is, 30 is less than infinity. And then we need to check for the base case, which is whether deletion is in our assumptions causable. It is. So this formula actually type checks correctly. And we can actually enforce it. Any questions so far?
So Mary, you mentioned that causable and enforceable are kind of mutually exclusive.
Causable and suppressible, yes, yes.
So is there a situation where you would want both? I'm trying to imagine a scenario like an application where you would want an event to be both possible.
So, I mean, usually when we find this is like if we have something like usage, like a very generic event, right? So in those cases, sometimes we want the usage to be both causable or suppressible. And for instance, data minimization case, you have to delete something if you're not using it, right? So you can force usage in order not to delete it, right? Something like that. But usage can also be refined into more fine-grained actions where one can be suppressible, one can be causable. So far we didn't need this to be. The only problem that we had was that actually it was like a note in one of the slides before, is that we actually distinguish events only based on their name, not based on their parameters, whether they are causable or suppressible. And we do not allow the same name to be both causable and suppressible for the sake of how our algorithm actually works, which is if we would get a formula like this, with E being both suppressible and causable, this will actually never be enforced, cannot be enforced. So this is kind of the reason why we chose this, and so far this limitation was not crucial. But thanks, actually, I did not mention that point at the beginning. Yes. So now we know that this formula is enforceable. How do we actually enforce it? So intuitively, how the algorithm works, I mean, I won't go into full details, but just the general idea is that it kind of maintains these sets of present obligations and future obligations. And present obligations are just these triples of a formula, valuation, and polarity. And for now, polarity, you don't have to think about it. It's just whether you need to cause something, if something has a polarity plus and you need to cause it, that's fine. If you have to suppress it, then you switch to polarity and then you cause the negation. Just a technicality. And you have a future obligation, which is the same as this triple, except that the first formula is not really, it's a function that maps from timestamps to formulas. Okay, so it's a kind of a parameterized formula. And these future obligations are useful because when we need to cause something in the future, we don't know exactly when, because we will only receive the timestamp later. So when we receive the timestamp, we plug it into the future obligation to obtain the present obligation of what we need to do now. Okay, so what the algorithm does at high level at the beginning, it just starts with a goal, and the goal is just a conjunction of all obligations, all present obligations. And this is just the original formula at the beginning. Then it decomposes these obligations into simpler goals. So it tries to cause things that are in the present, and things that are in the future, they are then computed as a new set of obligations for the next time point. So it returns three things: what to cause, what to suppress, and what to kind of defer for the next, for like better times. And I will not go through the pseudocode, but so here I actually show you all the cases needed to enforce the formula from before. So it has the implication, the for all, the eventually, and the always, and the base case. But let me give you an example. So this is the formula above. I just call it phi del for simplicity. And we have this current execution. We actually, as we are observing the execution, we don't know what's in the future. So just keep in mind that kind of as audience, you know that there will be a usage at some point, but we really don't know. The enforcer will only get informed about this prefix-wise. So we will start with receiving the deletion request from a user, right? So this is something that the system is reporting to the enforcer. Deletion request is neither causable nor suppressible, just observable. So the enforcer just updates its state and creates an obligation. An obligation, this is a future obligation because it's a lambda that just takes a timestamp and then doesn't use it, just produces the phi del. Then what it does, it evaluates it and adds this TP. For technical reasons, if you want to cause a position to happen in the trace, we just encode it with a TP, but it's not important. And then when we have this formula, we decompose it into two obligations. The obligation for a TP, obligation for the del, again. And what we do is we cause the time point, but the time point is already caused, so this is fine. And we are left with again, the same obligation, but present obligation here. So for future, so del actually has a top level always operator. So for the always is handled by essentially copy pasting the same obligation for the future, and then unfolding the formula here in a new obligation without the always operator around. And then applying other cases. So a case for all, So actually this formula is satisfied, it's fine. No, sorry, the deletion request is holds, right? So for this, we need to cause the deletion. And the deletion is a new future obligation that depends on the next timestamp. And again, we may need to introduce a time point in the trace. And we know exactly for deletion is 1 and 2 here. So we know also the evaluations for which we need to cause this obligation. So now we do the same thing again. We now assign these new obligations to the old obligations and do the same process again. We conjoin the obligations. We now know the new timestamp. The new timestamp is 10, but proactively, so we can still do something before the timestamp 11. So this is a proactive case. And what we do is we just plug the 10 here. We get the same obligation, the same formula, and then decompose into the same two obligations. Get the same obligations to enforce later, plus again the same thing, only now with a plugged-in valuation 1. We transfer this to future obligation. We put a lambda around it, and we wait for the next timestamp. Now we get to the next timestamp, 11. We plug it in, and you will see you get 29 here, and so on. And then we jump where we actually need to cause something. So we are at the timestamp 39. 39 with this plug. Then now we need to cause, right? So now we're at the timestamp 40. This is exactly 30 seconds away. We actually have an eventually with 0, 0 here, because when we plug 40 here, we get it. We reduce it, and now what we need to cause this. To cause this, it's just you cause the subformula. To cause the subformula, you cause the conjunction. To cause the conjunction, you get two obligations, TP and delete. You just put them in the causable set, and you provide it to the system. And that's actually a proactive step. So this actually, there was no interaction with the system based on an event. So we actually force the system to execute a deletion here. And then we continue proactive steps until we get to a reactive step, which is some use, which is completely unrelated to the formula. Questions?
So it seems that you have this requirement that delete must be within 30 units, but it seems that you always do it at the last possible time, right? But yeah, I guess there are scenarios in which you may want to have a more flexible enforcement, right? Say, okay, yeah, I do it maybe as soon as possible.
Yeah, so a very good question. There are kind of two properties that we want from the enforcers. I will come to that actually in a slide. But as kind of anticipation, enforcers should be sound, meaning when they modify an execution, the outcome of the execution should be compliant with the policy. But there is also another requirement which is less critical, but still nice, to be transparent. So if the system actually does something, then you shouldn't really do anything. You shouldn't really change its behavior if the behavior is already compliant. So the reason why we do this way is to ensure that we are transparent. That's the only reason. So that the enforcer is transparent. But I agree, if you want to do it non-transparently, which also some enforcers can do, then you can definitely cause it much more proactive. Okay. So I got to this point. So to be correct, now I'm just writing here kind of, I'm abusing notation. So imagine you had this like previous algorithm which returns corrections, and now you apply these corrections to the trace to get a new trace. This is essentially what this thing means. So it gets a trace from the system, and it outputs the modified trace. And now, given such an enforcer, we say it's sound with respect to some formula if this holds, that for that new trace, the formula is satisfied, okay? And then we have this another requirement, and that is that an enforcer is transparent with respect to a formula if essentially for all phi that satisfy the formula, the enforcer returns exactly the same trace. Sorry, for all sigma, so all traces that satisfy the formula, enforcer applied to the trace returns the same trace. So these are the two key correctness criteria, where I would say that the transparency is kind of in practice less important, but still important, that maybe you don't want to have unnecessary interventions in the system. So for soundness, we've actually proved that if a formula is in this fragment enf, then our enforcer has presented the sound. For transparency, actually, it's not the case. We need an even stricter fragment. And I mean, I would refer you to the paper to see that. But yeah, the general idea was indeed for some cases of temporal operators, the intervals needed to be even stricter. And yes, the implementation is as follows. You can actually try it out. This was published at CAV last year, and already this year we have an extension. So EnfGuard relies on a backend runtime monitor that can monitor enf specifications with some. It was slightly modified to support future obligations, which are kind of assumptions on the trace, and then gives you verdicts. And it just calls this monitor as a subroutine. Our proofs, of course, we don't prove that the monitor is correct, but we have certain invariance assumptions because this is not our tool. Some assumptions that we are fairly certain are satisfied, based on which we can discharge the theorems for the EnfGuard. And yes, the extended version, which actually is going to appear this year at CAV, also supports complex terms like user-defined functions, aggregations, and let bindings. So you can actually create a complex formula by just assigning it to a kind of invented new predicate name. And all this idea of analyzing whether something is causable, suppressible, translates to these let constructs quite elegantly, actually. So for the evaluation, we asked a couple of questions. First, we asked whether this fragment that we created, is it even useful? Like how many policies can we actually formalize, and how much effort it will take maybe to rewrite them such that they fit the fragment and their equivalent and so on. The other question is, what would be the event rate that the EnfGuard would support? So definitely it's a real-time enforcer. So there are actually some real-time constraints on how fast you need to be in order to enforce real-time properties, right? So the question is what is the bound after which the enforcer is not really real-time anymore, right? So what is the fastest system on which the enforcer can be applied? And then whether its performance improves upon the state of the art on the shared fragment of specifications, because on the current specification, it actually is the most expressive. So we actually have done, I'm kind of now mixing two evaluations. So this is from the latest paper, where we actually done this on 6 data sets. But the other data sets kind of required some other features that were part of the extension. So then I will just focus on the first data set called GDPR, which is actually a data set of real logs and real policies. There were actually 6 formulae that we could enforce. And we compared on that with the 4 other tools. So WhyEnf, which is just a previous version, enf-poly, which is a past-only enforcement tool, so only past-only formulas, and monpoly is actually just a monitor, which we just wanted to see how slower enforcers are compared to monitors, even though they completely solve different problems. Monitors just report violations, whereas enforcers compute how to correct them, which is a harder problem. And then you can see roughly the sizes of the logs and the event rate. So how many events per second in the log, or I mean, I think it's the opposite. It's how many seconds divided by events, I guess here. So the GDPR dataset contained the enforceable formalization of some core GDPR provisions. This is from a previous paper. And then also some actual real traces from a real world system. And then we also generated some synthetic traces just to also figure out, the performance much better. And these are the policies that we started from. Actually, you see there are not 6, there are 7. The problem is that this one is not enforceable. Actually, this one is non-transparently enforceable. If you just equals use every time you see a collect, it's fine. But otherwise, it's not in enforceable fragment. The other 6 are fine, and we could actually use them as they were. Like we did not need to rewrite them such that they fit the fragment, which we were kind of happy because that means that the type system was kind of permissive enough for what we needed. To understand the maximum event rate question. So what is the maximum event rate that can be supported? So what is the fastest system we can enforce on? We first need to understand the difference between timestamp time. So if you have a trace, we actually didn't have a system here. We had actually traces from a system. So we needed to kind of simulate a system running, right? So we had these traces with timestamps, and we needed to kind of reproduce them at the rate at which the timestamps occur in the trace, which then I need to point out is different than the actual real time, right? And we call it event rate, the number of events per time unit in a trace in terms of timestamp time. And ingestion rate, this is the actual ingestion, it's the number of events that you actually ingest per unit of real time when you are feeding it to the enforcer. And then we had this thing called acceleration, which is just we could actually fiddle with it to see if we speed up the ingestion of the same trace by speeding up by increasing linearly the ingestion rate. Then we could actually see hypothetically if we speed up the trace what are the fastest systems we can enforce on. And then what we measured was latency. This is essentially when you send an event to the monitor, start a stopwatch when the enforcer. Once you receive the command, you stop the stopwatch, and that's the latency. And then what we looked at is we would do an enforcement on a full trace, and then we look at the maximum latency at any point. And of course, we look at it as a function of acceleration. So we actually accelerate the trace at different rates, and then we see how the latency changes. So this is kind of the graph. Each color corresponds to a different formula that I mentioned. And you can see for some formulas, the latency which is shown there, so the colored ones correspond to the right-hand side axis. And you see that somewhere latency spikes much faster for accelerations than for the others. But definitely they spike above a threshold where essentially giving commands is too late already. And this threshold is this line here. So we could actually accelerate, so beyond just 1, which is we would get acceleration 1 means we are observing the system as it really produced the events. But we could go all the way to in the worst case formula somewhere here, right? So in between like 10 to the power of 5, 10 to the power of 5 to 10 to the power of 6, right? Then we also looked at the other tools. So I mentioned the monitor and I mentioned another enforcer. And there we again looked at the average event rate that we can achieve for a certain bounded latency. And actually our tool was the best for everything except two formulas, where the pass-only tool was better. And actually it makes sense because the pass-only tool had much simpler data structures for enforcement. And of course, these were pass-only formulas, so we were kind of disadvantaged from the perspective of expressiveness. But other than that, in other cases where the formulas were not supported, we were better, even better than the monitor, even, which was surprising. Okay, any questions? Yeah.
Yes. Can you please go back to the auto evaluation table? Because this yeah, this one. In the column there is loss. Loss is the time series of events. It's the loss for the events.
Sorry. Yeah. Okay. So this is a bit of a problem with terminology. So this is the number of traces that this data set contains. Yeah. And then this is the size of the, I guess, the maximum size of the traces. So here that's the only trace, but here the maximum size is one of the traces, is this.
And another question. In the next slide, if I remember correct, yeah, here. When you say formalization of core and GDPR provisions, are they done manually?
Yes.
And do you know if there is some research automating the formalization of policy based on?
I mean, not specifically in the case of GDPR, but in general, I mean, these days, quite a lot, LLM work, right? With the,
I think you can pre-LLM. I know that we
yeah, okay, something like specification inference, right, or like specification mining, right, where you can actually execute system like a system, and then like based on the observation, start building like an automaton that describes this. But these are actually, I'm not sure about like temporal logic formula mining, but possibly as well. Yes, I'm not sure. But for sure, there are some automatic approaches. Not sure how well they work. I mean, it would be nice to see if they coincide, or if we use some form. So I also know a lot more detailed. So these are very simple formalizations. There are also much more detailed formalizations that even come with their ontologies of different events and how they relate and so on. And it would be nice to maybe kind of see how the automatic ones would fare with respect to these, which are quite detailed and also manual. Hopefully kind of ground truth, if there is any ground truth. Yeah, in terms of interpreting what law says. Yeah. Thanks. Any other questions? Then I would just mention some interesting future work related to this, and also some other projects that I'm involved in. So further optimizations of mGuard. So I mentioned this, that there was another enforcer that was supporting only pass-only operators, temporal operators. And indeed, it's faster. And I mean, fair enough. It uses simple tables and relational operators internally for that, which is much more efficient than what we use. So we rely on WhyEnf, and WhyEnf uses an extension of BDDs to compute evaluations, which are actually much more heavy-duty operations. It would be nice to have, again, also a fragment within a fragment, where if you recognize that a certain subformula belongs to the fragment where you can use a simple data structure, then just use that. And then beyond that, just generalize to so you can take a table and just build a BDD out of it very easily. And then you know, continue with the, you can kind of get the best average case performance there, I guess. That would be one idea. And I mean, we are also looking into it right now with a student. The other one is using this in larger software. So actually building this entire loop of observing things that are about to happen, computing enforcement decisions, going back and then enforcing. And then even not relying on enforceable as a specification, but even having a higher level specification for not only like specifically legal specifications, but even other more general specifications. And then also thinking about, so when we actually also are currently working on this and have some encouraging results. The thing is, this instrumentation actuation loop that is around the enforcer and the system is kind of built ad hoc. And the question also is like, how much problems can we introduce by just composing these things ad hoc, right? What are the guarantees that this instrumentation and this actuation need to satisfy such that we can guarantee that the composition actually is compliant? And then we also are working kind of on that, like figuring out kind of what are the sound and transparent instrumentation, as you would think, and they are actually independent of the policy, unlike the enforcer. Also, it's kind of interesting. We also noticed with developing this theory that there are certain specifications that are monotonic or anti-monotonic in some events. For example, if you would have consent and use, and then you want to say you are forbidden of using something unless you have a consent in the past from a user, and then your instrumentation is broken and doesn't log all consent. If your enforcer is sound, you're still fine. Overlogging consent that is not there, that users did not provide, is bad. But if you have something like an anti-monotonic relationship in some events, then you can even go through your like instrumentation and prove, okay, we are doing a sound but incomplete logging, and this is fine. And then, of course, there is other work on runtime monitoring, model-driven security and privacy, and information flow control, which I would like to talk about maybe during the apero. So that's it. Thank you for your attention. If you have any questions.